In section 4.2, we are going to continue to expand our understanding of probability, and we're going to take a look at something called the addition rule of probability. Now, the addition rule requires us to understand this concept called mutually exclusive events or disjoint events. Now, two events, it says, are mutually exclusive events or disjoint events if they cannot occur at the same time, i.e., they have no outcomes in common. From a visual standpoint, we use a Venn diagram to illustrate this. If this box right here represents our entire sample space, every possible outcome fits into this box. Let's say that we have an event that is defined by this circle right here. So this circle says this portion of my sample space fits some sort of condition, right? And let's say that this circle here represents some other condition or some other event that can happen within my sample space. Visually speaking, these two circles don't overlap. All of the outcomes inside of this event are different than all of the outcomes inside this event. An example of that might be something to the effect of this right here being a deck of cards, and these represent all of the hearts. And this right here, this event represents getting a diamond, right? In a deck of cards, there is no card that is both a heart and a diamond. They are mutually exclusive. You can't draw a single card and have that card be both a heart and a diamond. Just not possible. So that's the concept of mutually exclusive, right? If there is overlap, we would represent that in a Venn diagram like this, where this portion represents that it is possible that certain outcomes exist in both events. Take, for example, this being hearts and this being number card. Are there hearts that are number cards? Well, yeah. Are there hearts that are not number cards? Yeah, the Jack, King, and Queen. Are there number cards that are not hearts? Yes, plenty of those. But there do exist some cards that are both hearts and number cards. So this overlapping region is what would visually represent that. Let's look at a couple more examples that determine if they're mutually exclusive. Let's say you're randomly selecting a female student and randomly selecting a student who is a junior. Are those mutually exclusive? Can those happen at the same time? Can you select a student that is both a female and a junior? Yeah, you can. So those two events are not mutually exclusive. What about randomly selecting a person that has type A blood, randomly selecting a person with type O blood? Can you randomly select a person that has both type A and type O blood? No, you can't. You only have type A or type O blood. So we would say that that is mutually exclusive. What about this next one? Rolling a die and getting an odd number, rolling a die and getting a number less than 3. Is getting an odd number and rolling a number less than 3, are those two things mutually exclusive? I don't think they are. Okay, not because what's a number less than 3? Well, what about the number 1? That is both less than 3 and it's an odd number. So not mutually exclusive. What about this one? Randomly selecting a person who is under 21 years of age. Randomly selecting a person who is over 30 years of age. Is it possible to randomly select someone that is both younger than 21 and older than 30 at the same time? No, it's not. So we would say that these are, it is mutually exclusive. These events are. Great. So now that we understand this concept of mutually exclusive, we want to take a look at the addition rule. And what we're going to find out is that the addition rule is dependent upon whether the two events that we're looking at are mutually exclusive. Here is addition rule number 1. It says this: when two events A and B are mutually exclusive, the probability that A or B will occur is the probability of A or B equals the probability of A plus the probability of B. So in other words, here's what it's saying. If you want to find the probability that this happens or this happens, you simply find the probability of each of those happening and add them together. The addition rule is used whenever we have the concept or the scenario of or. The addition rule is connected with or. What is the probability of this or this happening? Okay. So let's take a look at an example. The endangered species. In the United States, there are 59 different species of mammals, okay, that are endangered, 75 different species of birds that are endangered, and 68 species of fish that are endangered. Okay? Here's the question. If one animal is selected at random, find the probability that it is either a mammal or a fish. Is it a mammal or a fish? Here's the question. Are these two events mutually exclusive? Because this rule is dependent upon that. Is it possible for something to be both a mammal and a fish? No, it's not. They're mutually exclusive events. Okay? So here's what we want to do. If I want to randomly select a single animal, and I want to find the probability that that animal is either a mammal or a fish, what do I need to do? Let's first define some things. Let's let event A equal mammal. Let's let event B equal fish. We want to find what is the probability of A or B. What is the probability that I randomly select a single animal and it is either a mammal or a fish? Well, it says that it equals the probability of A plus the probability of B. Okay, well, I can figure out each of those. What is the probability of A? Well, the probability of getting a mammal. Well, how many mammals are there? There's 59. So 59 total possible outcomes within my sample space will give me a mammal. But what is my total sample space? Well, I know that there are 59 mammals plus 75 birds plus 68 fish. That gives me a total of 202 different animals. So I know that 59 out of the 202 are mammals. Okay. Well, what about the probability of B, fish? Well, how many fish are there? It's said that of those that are endangered, 68 of them are fish. So 68 out of, how many do we know there are? 202. So we've identified the probabilities of each of our outcomes, but I want to know the probability of randomly selecting one and it being fitting into either this outcome or that outcome. Well, we simply know that that equals adding those two together. So that's going to be 59 over 202 plus 68 over 202. So, well, common denominator, I'm just going to add across the top 59 plus 68. I'm getting 127 all over 202. Now, a little bit easier to understand that in the context of a fraction or as decimal. So I'm going to do a decimal really quick, and I'm going to round that to 3 decimal places. So 0.629. This equals 0.629. As a percentage, that's 62.9%. So what can we say? The probability that we randomly select one animal and it's either a mammal or a fish is 62.9%. Great. Let's look at another example. Favorite ice cream. In a survey, 8% of the respondents said that their favorite ice cream flavor is cookies and cream. 6% say that they like mint chocolate chip. If a person is selected at random, find the probability that his or her favorite ice cream flavor is either cookies and cream or mint chocolate chip. So let's define a few things. Let's say that A equals, what's the first one? Cookies and cream. And let's say that B is equal to that next one, mint chocolate chip. Okay. Well, I want to find what is the probability that I randomly select a single person and their favorite ice cream is cookies and cream or mint chocolate chip. Well, I know that that simply is the probability of A plus the probability of B. Well, what is the probability of A? Well, it says the probability of someone being randomly selected and their favorite ice cream is cookie and cream was 8%. So I'm just going to say the probability of A is 8%. What's the probability of B? Mint chocolate chip, it said 6%, didn't it? So it's as simple as saying the probability that I randomly select someone and their favorite ice cream is either cookies and cream or chocolate and mint is equal to 8% plus 6%, which equals 14%. In other words, what we're saying is that if I randomly select somebody, I know that there's a 14% chance that they're going to fit into the category of someone who likes mint chocolate chip or cookies and cream. Not both, but one or the other. Keep that in mind. We're looking at things that we're not looking at two events happening at the same time. We're looking at one event fitting either into the first category or the second category, the event A or the event B. Okay. So there's some examples of the addition rule when the events that we're looking at are mutually exclusive, meaning they can't occur together. But what about the scenario in which the events aren't mutually exclusive? What about if they are able to happen together? Well, let's take a look at this. The rule says this: if A and B are not mutually exclusive, then the probability of A or B is equal to the probability of A plus the probability of B. So far from here over, nothing's changed. But then we have this minus the probability of A and B. Okay, let's take a look at that a little closer. Let's take a look at that in the context of a Venn diagram again. We know we're now dealing with two events that are not mutually exclusive. So let's let this represent A and this represent B. What we're doing in the addition rule is we're saying let's add up all of this, event A, plus all of B. But notice this: if those two events overlap, what is happening in this middle space here? This middle space is getting counted twice. That middle space represents both A and B occurring at the same time. Take a look at this last piece that we're subtracting. If we're double counting the scenario of when A and B are happening at the same time, don't we have to subtract one of those scenarios away so that it's not being double counted? Okay. So what does this look like practically in a couple examples? Let's look at this one right here. It says this: a single card is drawn at random from an ordinary deck of cards. Here's what we want to do. Find the probability that it is either a 9 or a diamond. Okay. Well, we can already see here these are not mutually exclusive events. It is possible to get a card that is both a 9 and a diamond. Okay. So let's let event A equal getting a 9. Let's let event B equal getting a diamond. So we know that the probability of A or B for events that are not mutually exclusive is the probability of A plus the probability of B minus the probability of A and B. Excuse me. Okay. So what is the probability of A? The probability of A, the probability of getting a 9. I know that there are 4 cards in the mix that are 9s. The 9 of hearts, the 9 of diamonds, the 9 of spades, the 9 of clubs, out of the 52 cards. Well, I also know that the probability of B, the probability of getting a diamond, there are 13 diamonds out of the 52 cards. But lastly, what is the probability of getting a 9 and a diamond? The probability of A and B. Well, how many cards fit that scenario? How many cards are in that deck that are both a 9 and a diamond? Well, there's only one 9 diamond out of the 52. So the probability of getting a 9 and a diamond in the same card is 1 out of 52. I now have the pieces for the puzzle up here. Probability of A, 4 out of 52 are 9s, plus 13 out of 52 are diamonds, but when I add those together, I'm double counting. The 9 of diamonds is in both of those fractions right there, both of those probabilities. So I'm double counting it, so I need to subtract that 1 out of 52. 4, so I've got the common denominator across the bottom. So 4 plus 13 is 17, minus 1 is 16. So 16 over 52, I think that ends up reducing to 4 over 13. 4 over 13. So that 4 out of 13, if we get that in a decimal really quick, 4 divided by 4 divided by 13 is 0.308. 0.308 or 30.8%. So there's a 30.8% chance that if I randomly select a card from a deck of cards that I'm going to find it is either a diamond or a 9. Great, let's look at one final example of this concept. Selecting a medical staff person. It says this: in a hospital unit, there are 9 nurses and 5 physicians. Okay. Of those, though, 7 of the nurses and 3 of the physicians are female. If a staff person is selected, find the probability that the subject is a nurse or a male. Okay. We only have a portion of the information that we need, but here's what we're going to do. There is a really convenient way when you're dealing with 2 different variables. The variables that we're dealing with, right, are whether they're a nurse or a physician and whether they're male or female. Here's how I'm going to break this up. Okay. I'm going to say physician and nurse, and then male and female. Now, what do I know? In a hospital unit, there are 8 nurses. So the total number of nurses, I'm going to put right out here, 8. And then what did it say the total number of physicians were? 5. So total number of physicians, 5. Now it says that 7 nurses and 3 physicians are female. So 7 nurses, I'm going to put a 7 right here next to nurse and under female. And I'm going to put a 3 right here that's next to physician and under female. Now I can backtrack and say if 3 of the 5 physicians are female, that means that the other 2 are males. And if 7 of the 8 nurses are female, that means 1 of them is a male. And then take a look at what I can do now. How many total females do I have? I have 10. How many total males do I have? I have 3. But here's the important part of why this all works and how it's helpful to us. What is 3 plus 10? It's 13. What is 5 plus 8? It's 13. So we know that we have a total of 13 medical staff persons. I know that 3 of them are male, 10 of them are female. I know that 5 are physicians, 8 are nurses. And I even know the breakdown now by using the data and backtracking. I know how many of them fit into each one of those unique categories. It says this, though, what the question that we're asked is, if a staff person is selected, find the probability that the subject is a nurse or a male. So I'm going to let A equal nurse. I'm going to let B equal male. So what is the probability that I randomly select a person and it's a nurse or a male, A or B? Well, that's going to equal the probability of A plus the probability of B minus the probability of A and B. Excuse me again. Okay. Well, what is the probability of A? What's the probability that I randomly select a person and they are a nurse? Well, how many nurses do I know there are? 8 out of how many total medical staff? 13. So the probability of A is 8 over 13. Okay. What about the probability of a male? Well, how many total males are there? Well, there's a total of 3 males out of the total medical staff of 13. So the probability is 3 over 13. But what is now the probability of A and B? What does that equal? Right? Because we need to subtract that off of that, because the outcomes of a nurse or a male are not mutually exclusive. You can randomly select a single person and they are both a nurse and a male. They are not mutually exclusive. So let's look at that. Let's look at the male column and the nurse row. Where do those overlap? Well, right here. I have one of my medical staff that fits both category of male and the category of nurse. So that means that I have 1 out of 13 where it is both a nurse and a male. I can now find out or figure out the rest, my total probability. The probability of A equals 8 over 13. The probability of B is 3 over 13 minus, what is the probability of A and B? 1 over 13. So this equals common denominator of 13. 8 plus 3 is 11, minus 1 is 10. So leaving it as a fraction, 10 out of 13. So what is the probability that I randomly select a person and I find that they are either a nurse or a male? Well, 10 out of 13 times, that's going to happen. So this is the addition rule and how to do the addition rule depending on if your events are mutually exclusive or are not mutually exclusive.